Welcome to The Explainer. Today we're setting our sights on Messier 12. At first glance, it looks like a beautiful, dense ball of glittering stars, a kind of star city. But it's actually hiding a pretty dramatic story. A story of cosmic theft that astronomers have been piecing together for years.
So, let's get right to the heart of the mystery. When astronomers look at these ancient star clusters, called globular clusters, they expect a certain mix of stars. But M12, well, it just doesn't follow the rules. It's kind of like a town where all the youngest residents have simply vanished. So the big question is, where did all its small, lightweight stars go?
And to get our bearings, this cluster, which also goes by the name NGC 6218, is a long, long way from home. We're talking about 15,700 light-years away from us, sitting in the constellation Ophiuchus. Now, it's part of our own Milky Way galaxy, and its orbit around the galactic center, well, that turns out to be a huge clue in its story.
So, what is this big secret M12 is hiding? It's not something you can just spot with a telescope. To really get it, we need to talk about how stars are sorted in a cluster. It's a concept astronomers call the mass function.
Okay, think of a mass function like a city's census. It tells you exactly how many heavy, medium, and lightweight stars the cluster has. And normally, what you find is a ton of small, low-mass stars, and then fewer and fewer as you get to the really big, heavy ones. It should look like a pyramid with a really wide base.
And here's where it gets really weird. On the left, you see what a typical cluster should look like, that nice pyramid shape, full of the little guys. But on the right, that's Messier 12. Its mass function is bizarrely flat. It's like the entire bottom of the pyramid has just been sliced off. It is seriously lacking in low-mass stars.
You know, the prime suspect in this cosmic crime is actually our own galaxy. As M12 makes its long journey around the Milky Way, our galaxy's huge gravitational pull tugs on it. This is called tidal stripping. And the easiest stars to steal are the lightest ones on the edges of the cluster. So over billions of years, M12 has been slowly bled of what could be millions of its smallest stars.
But believe it or not, the mystery doesn't stop there. Cracking the case of the missing stars took two very different, very powerful sets of detective tools. And what they found revealed an even deeper secret about how M12 was actually born.
So you've got two teams on the case. On one side, you have astronomy. These are the surveyors. They track exactly where the stars are moving. On the other side, you have spectroscopy. Let's call them the chemists. They analyze the light from stars to figure out what they're made of. And putting their findings together, that's how you reconstruct a cluster's entire history.
So, the astrometry team went first. They took pictures of the cluster years apart and then compared them. This let them measure the proper motion of thousands of stars. See, the real members of M12 are all flying through space together, kind of like a swarm of bees. But the other stars, the ones just in the background or foreground, are all moving in different directions. This let the team create a definitive list of who actually lives in M12.
Before this painstaking work, the view was just a total mess. Trying to study M12 was like trying to study one family in the middle of a packed city square. You just couldn't be sure who actually belonged there and who was just photobombing the picture.
And here's the aftershot. With all those imposters removed, you can see just how powerful this technique is. Scientists now had this perfectly clean sample of 3,725 confirmed members. And that meant the chemistry team could finally get to work with total confidence. All right, so now that they had a clean list of suspects, the spectroscopy team could start analyzing the stellar DNA of M12 stars. And what they uncovered was absolutely stunning. It pointed to a complex, multi-stage birth for the cluster.
This quote from the research paper really gets to the heart of it. By looking at the chemical makeup of these stars, astronomers found a weird pattern. And it was a pattern that couldn't have been created by the stars themselves as they aged. It had to have been there right from the very beginning, imprinted on the gas clouds that formed them.
So here's the chemical fingerprint. It's called the sodium-oxygen anticorrelation. Think of it like a seesaw. When a star has a lot of sodium, it has very little oxygen, and vice versa. There's only one way to explain this. There must have been an earlier first generation of massive stars that polluted the cluster's gas. Then, a second generation of stars formed from that enriched, recycled material.
So, the takeaway here is huge. M12 isn't just a simple family of stars all born at the same time from the same stuff. No, it's a multi-generational metropolis built in at least two separate phases way back in the early days of the universe.
And you can actually see physical evidence of this. This chart compares the stars in M12 to another cluster. See that band of stars in the middle panel? That's a specific phase of aging called the horizontal branch. For M12, it's shifted way over to the left, into the blue. And for a long time, that blue shift was a real puzzle for astronomers.
And the chemistry gives us the answer. That second polluted generation of stars isn't just richer in sodium, it's also richer in helium. And a higher helium content makes a star burn hotter and look bluer as it gets older, which is exactly what we see in that strangely blue horizontal branch. The cluster's hidden chemical history actually dictates its appearance today.
Okay, so we've got a star-stripped cluster with two different generations of stars. Why does this one star city matter so much in the grand scheme of things? Let's tie it all together.
First off, this is just a beautiful example of how science works. The hard work of the astrometry team, our surveyors, gave the spectroscopy team, our chemists, the clean data they needed. They could be certain that their incredible discovery of two populations was real, and not just some contamination from random background stars.
This table really sums up what makes M12 such an amazing cosmic laboratory. It has a violent past, which we can tell from its missing stars. It has a complex birth, revealed by its two chemical populations. And these two facts are connected, telling us a much deeper story about how our galaxy was built.
So the big takeaway here is that these ancient clusters aren't just simple static objects. They are dynamic places that have been shaped by both how they formed on the inside and by their rough environment on the outside. Studying battered, multi-generational clusters like M12 is one of our best windows into the chaotic early days of the Milky Way.
And that leaves us with a really fascinating thought. The discovery that these primordial building blocks of our galaxy were themselves built in stages, well, that completely changes our perspective. It suggests the story of how our galaxy formed is way more intricate than we ever imagined, with who knows how many secrets still locked away in these ancient star cities.